started. Again, this is part of the lecture series put on by Science in the News. We're an entirely graduate student and volunteer-run organization that seeks to build bonds between scientists and the general public and encourage scientists to communicate their work and their research in a way that's accessible and hopefully, inspiring. And so you're joining us tonight for one of our lectures here with our speaker tonight, Stephen Teresi, who will be speaking to you about artificial intelligence in material science. And so with that, I will turn it over to him and enjoy your night.
All right. Oh, thank you very much for the introduction. I'm very happy to be here and glad that people came out to learn a thing or two about something that I'm pretty excited about. So before I dive into the content of my talk, I'd just like to give a little bit of a biographical background about myself. So I'm from upstate New York, between Poughkeepsie and Albany, if that means anything to you. And I'm a physics graduate student at Harvard. For undergrad, I was at the University of Rochester, also in upstate New York, graduating a few years ago, and my background there was in physics and math. And so I still do physics, but increasingly I've been moving more towards material science for some reasons that I hope you'll sort of understand my excitement for in just a second. But my research has taken me all over the place. So these are all places that I've been at in various projects. But a common theme between these different projects has been using computers to better understand certain scientific processes or phenomena. And so this talk is kind of an extension of all of that. So first, my talk will be organized around the following three themes. So first, I'm going to tell you a little bit about artificial intelligence 101. I imagine this is something that maybe caught your eye about this talk. It's something that a lot of people are talking about. It's something that's very exciting. I'll talk a little bit next about materials of the future. So I'll give you an overview of some of the motivation that we have for pursuing certain problems in material science, as well as certain materials that we're very excited about because they might have the possibility to better welfare for humankind in some pretty cool ways. And finally, in the third act, I'm going to tie together the first two and explain how computers can help be a scientist's best friend for a lot of different really interesting applications that are related to the first two parts of this talk. So let's start with AI 101. So why this talk, right? There is a lot of excitement right now about artificial intelligence. You probably have seen it, perhaps in passing, or maybe you have some familiarity with it, or having taken a class or two. But there have been a lot of very famous, sort of iconic science of computers in more and more domains that it may not have been so obvious that computers could do so well at, such as this program AlphaGo, which defeated a World Go champion a few years ago in 2016. A follow-up sort of study from that same group, a program called AlphaZero. Was a program that learned how to play Go and chess just by playing against itself. So it never even had to watch a human make a single move. They just showed it the rules of the game, let it play against itself, and after thousands and thousands of iterations, it was able to play at an expert level. Pretty impressive stuff. Artificial intelligence, of course, gets thrown around a lot in the news, and that has its own set of connotations that's been given to us from popular media, maybe sci-fi, or even just what the phrase itself sort of connotes. A lot of issues that it touches on. Increasingly, this being paid how artificial intelligence being used for decision-making processes of various, levels of societal importance, like credit scores, or whether we give somebody a loan or not. Questions of fairness and discrimination are very important to keep in mind. There's increasingly many articles about the usage of artificial intelligence by government actors that people are paying a lot of attention to and spending a lot of time thinking about. And there are also a lot of really interesting and exciting applications of AI in science, technology, medicine, transportation, things like self-driving cars. And so hopefully in this talk, we'll get a chance to all learn about it together. And I can kind of, share a few interesting highlights, both from my field and beyond it. So an obvious place to start is, what do we mean when we say artificial intelligence? And how does it contrast with human intelligence? Because that might help us get a handle on how we can start to think about AI as a concept. So let's start with the more familiar one, which, to all of us is human intelligence. So what sort of characterizes human intelligence? For the purposes of this talk, what stands out to me is that human intelligence is very versatile. If I had to liken it to a tool, I would say like a Swiss Army knife, because our brains are really remarkable sort of devices that allow us to do things like read a book, We can ride a bike, maintain our balance in response to rapidly changing sort of visual sensory stimulus. We can calculate the tip on a bill. We can tell and understand jokes. Our brains are also, on top of all of this, keeping us alive. They're timing our breathing for everyone in the room right now, governing many different cycles that are keeping you alive. Basically, human intelligence can do a lot of different things. And so a natural question is, okay, when I say artificial intelligence, will computers necessarily be able to think like this too? And so there are some people who are researching like general AI, general artificial intelligence, but for the near future, so in the ways in which AI is being employed today, and for at least next couple of years, computers are probably not going to be thinking like this. So what we're seeing is instead specialized tasks that are being executed by AI-based programs. So if I have to liken this to again, the tool analogy, it would be more purpose-built ones like a scalpel or a hammer or a corkscrew, which are all useful for individual tasks, though you wouldn't want to use this to pound nails, for example. Certain AI-based tasks that we already see are like identifying faces in photos, like in social media, translating speech into computer instructions if you speak to your Amazon Alexa, or making movie recommendations based on what you've watched, such as on Netflix or on Hulu. So again, for now, caveat, AI is mostly seeing implementation in terms of highly specialized tools that automate and or outperform human intelligence. So, automation is also pretty miraculous, but outperforming is also really cool. Human intelligence at one thing in particular. So to go a little bit deeper on this AI theme, there's no necessarily one singular definition, but one might read, they're programs which attempt to mimic the cognitive function of humans. And so I chose this word function for a reason, because function can, the way I'm thinking about it means, how it can get applied to a goal or a certain task at hand. But function can occur by different means. So for example, if the function of a bird or an airplane is to fly, both of those get there through very different, they both have very different routes to getting there. Birds' wings are light and they flap and they're made of feathers. Airplane wings are immobile, but they have, a jet engine that is, of course, made of metal. And if I could put a third thing over here, which would be a helicopter, which doesn't even superficially resemble a bird or an airplane, yet still manages to fly through its own function. So even if a human can play chess as well as ride a bike and lose to a computer, doesn't necessarily mean that the computer is thinking about like a chess game in the same way that human is. And so again, what I'll keep coming back to later on in this talk is that there's a lot of promise for AI in the sciences in particular. So one phrase that I heard, which I really liked, was that we want to move from AI, artificial intelligence, to intelligence augmented. So if AI tools can help us either see patterns where we couldn't understand them or notice them before, or if AI programs could help us plan experiments to discover new materials or devices, or even in more pedestrian applications, like if a AI program can help people drive. Like it doesn't even have to be like a computer replacing a driver. It could just be let's say like your 16-year-old son doesn't necessarily know what to look for in a driver in front of him that signals that maybe the driver is driving unsafely and that you should be cautious. But if the computer has studied millions of hours of driving and has a sensor that can detect that the driver in front is behaving erratically, then maybe it could like flash an alarm or something. That's an instance where the computer has taught you something, and it has is augmented your intelligence as a driver. Helping doctors make diagnoses. Computers and AI programs in particular are really good at sniffing out patterns where it may not be so obvious to human sort of modes of thinking. And so there's some really interesting cases with this where AI has been shown to have a lot of promise for assisting doctors in sort of making trends or drawing trends or conclusions from data. But we'll come back to this concept a little bit later. For now, I want to focus a little bit more on some examples of how AI programs work, because I think it would be very instructive, as well as feeding into the rest of the talk. So let's zoom out all the way to the top. So how does a program, forget AI, conventional programs, how do programs in general work? The way we're going to think about it for this talk is that from a program's perspective, ultimately, it's just something that maps inputs to outputs. So for example, if you were to take a very simple device with a very rudimentary sort of computer inside, like a 4-function calculator, the input could be, the button press 2, pushing the plus button, pushing the to button, then pushing the equals button. And that's all the calculator has seen. And then it knows from there that the output that it's supposed to deliver is the number 4. And so I'm going to build on this theme, but like one thing that's kind of neat is that an important point here and later is that our program here, our calculator, doesn't have to necessarily know what it's doing. It doesn't have to have a sense of what 2 is in a profound or contextual way. The calculator doesn't know if I'm calculating the bill or calculating the mass of the sun. It's just mapping inputs to outputs. And programs all the way on much higher levels of complexity can also be thought of in this abstract way. For example, if you were to use a search engine, so named because they're not sponsoring our talk, like Goggle, where you could punch in, a question that you want information about, where your input here would be, I want to know the movie times for Road Adventures 5. The answer that comes out, or the results of that sort of search, are the output of your program in question. Or here, this would be the show times. And so, I'm saying that really we can think about any program in this way, where ultimately, this swiggle represents some input depending on the program, and this swiggle represents some output, also depending on the program in question. And so even AI-based programs can be thought of like this. So as far as how we make programs, really the way I've defined it, basically all of the hard part comes right here in this arrow. And so the job of computer programmers is to write rules for the computer to follow. So an example of sort of rule kit that our calculator would be following is that, roughly speaking, translated to English, we could think of it as saying, somebody sat down and taught the computer, look, if you get a number, a plus sign, and a second number, then it equals, add the previous 2 numbers together and put it on the screen, right? So how do AI-based programs differ from this? So I'm saying that the magic happens in this arrow where instead of sitting down and explicitly writing out rules for the computer to follow, we instead kind of shift the goalposts, and we are now finding a way to let the computer learn its own rules. So lots of resources can be necessary to accomplish this task, but in certain cases, you're actually we can get some pretty miraculous and magical results from this. So let's talk a little bit more on how a computer program would actually learn the rules to perform some kind of task of interest to us. So first of all, they need to have a complex, flexible internal framework to be able to learn those rules. So an example that I'll put in a little bit is how we're train a program to identify images. So the input to this program would be an image, but we think of an image as being worth 1,000 words. We see it as a splash of colors that represents something to us. But the way the computer sees it is a series of pixels and pixels being a bunch of tiny dots of colors, and then a series of numbers that describe those colors. So we see an image, and the computer will just see a bunch of numbers describing that image. And so again, under the hood, our AI program would be a large set of rules, which ultimately turns a set of colored pixels into an output. And so these rules can get quite complicated. So we won't talk about them too much, but I wanted to comment a little bit on how computers can kind of make sense of images. One kind of AI-based program can, for example, learn global patterns as well as through an image. So I thought this was a really interesting case because, if I were to ask you, where's the face in this photo, it's pretty clear that, Mona Lisa is right there. That's what we're looking for. But a computer is kind of, a computer that's working in this way is kind of doomed to look at it by sort of scanning through. Is there a face here? No. Is there a face here? No. Is there a face here? No. And so on until once we got around here, it started to be like, oh, this is starting to look like a face. I think the face is over here. And so the thing is that for example, if we have a program that's concerned with faces, the patterns that the computer learns can come close to being interpretable in the same way that humans look at faces. For example, such a program might learn how to recognize noses by passing over a sort of nose pattern over the entire image and then looking for matches. But one thing I'll touch on a little bit later, something I want to mention now, is that these sort of patterns that a program might learn can correspond to what humans interpret and how humans look at photos, but they don't necessarily have to. And that's part of actually the power, is that they can look at things in a slightly different way than we would. Again, think about the bird in the airplane. So the next thing is that the kind of programs I'm talking about today will learn where we reward correct guesses and fix mistakes that the program makes. So I will now walk through an example of how it might look if we were to train an image classifier program to tell the difference between these two dogs. So I'd like to introduce all of you tonight to Pippin on the left, that's my dad's dog, and Fifi on the right, that's my mom's dog. So note that for humans, when it comes to identifying Pippin or Fifi, one photo is enough. I can show you one image of both of these, and you're like, okay, I've got their number. I know who we're looking at now. Because we can already look at this and bring all of the sort of knowledge that we carry with our brain to understand a bunch of rules from the outside. You can see that, okay, Pippin's got a black coat, Pippin is Shar-Pei, Pippin has a fat snout and small ears. Meanwhile, Fifi is a brown coat, is Pit Bull Shepherd mix, has a long thin snout and big ears. Now, a conventional sort of rules-based program where we would sit down and teach a computer to look at this image and understand what it's looking at would be pretty complicated to write up. For example, do we have to sit down and teach the program to understand that this is carpet, whereas this is part of the dog? That this this is a shadow. This is also just out of frame, but this is where the dog's coat has ended over here, or that these leaves are not necessarily part of the dog. We have to teach our program to see snouts, to understand different shadows and lighting configurations. There are parts of Fifi here that are sort of dark like Pippin, but it doesn't necessarily mean it belongs to the same dog. So this could get very out of hand very quickly if we wanted to do this. It's not necessarily impossible in principle, but sort of the promise of AI is that we get to sort of shift the difficulty somewhere else. And that we get the AI programs learn their own rules for identifying the two dogs and telling them apart. So moving on, if we wanted to construct such a program, we would have to start with a data bank of photos. And so, by the way, this data bank does exist. It's the Facebook Messenger thread with my family. And so we do have, let's say we have a database of photos of the two pups. And so then we could set up our AI program where we have configured it to go from our input, which here again is a photo, just a splash of colors, just a series of numbers describing a photo. And we set it up so that the output will be one of two names, so either Fifi or Pippin. And so in between, we would start with a program in a sort of blank slate configuration where it hasn't learned any rules yet to tell the dogs apart. So again, remember, under the hood, it does have the ability to learn potentially many, many complicated mathematical rules for turning an image to a guess as to which dog we're looking at. So we would start by hitting it with a photo of Fifi, and then we would say, okay, program, what do you think? And so if the output happens to be correct, now remember we're in the blank state stage, so this was most likely just a random guess, we would say, okay, that was correct. So now whatever rules went into making this correct guess, try to adjust your rules towards this answer. So next time, when you see an image that looks roughly like this, whatever that means to the program, try to associate, certain patterns with Fifi. So then if we were to feed in an image of Pippin, we would wait to see what the program says. And if it happened to output Fifi, we would see that that was incorrect. And so then what we would do is we would push that info back to the program, and we say, okay, that last guess was incorrect. So now adjust your rules away from that answer. So I don't know, what did this photo look like Fifi to you, but try to figure out a way to sort of get it right next time. And so then from there, maybe next time we show it a photo of Pippin, it would hopefully get the answer right, which would again result in positive feedback to the program. And so then this process would repeat automatically. So it would, potentially thousands or even millions of times, however long it took for the program to get to a sort of robust level where it could identify images that hopefully, it hasn't seen before, and to do so correctly. And so I want to pause here to note that there are two massive sort of things that I've assumed away here, but that are super, super important for how these models get implemented in real life. So basically, data and processing power is king for making these models and making them actually work in real life. So again, if you were to be a large search engine or a social media website, both with trillion-dollar valuations. These are the perfect sort of people to, this is where that trillion-dollar valuation comes from. It's not just from like event descriptions and photos of your grandkids, but it comes from the fact that you need a lot of data to do robust learning. So we want to have a program that can identify these dogs in a variety of different lighting situations, angles, maybe from the side, from behind, etc. And also, depending on what we're trying to do, if the task at hand is extremely complicated, this AI program can get quite complicated. And this process of automation can take a very long time. So both of those things require a lot of processing power. And so that's where that's sort of why these guys are able to extract so much value, is because they have access to these sort of resources in droves. So yeah, sort of this sort of matters for understanding how like society is going to organize around all these gains in AI. But now, so I want to come back to the model. So let's talk about what would happen if we threw our program a curveball. So if we were to throw in this guy, who is this? This handsome fella, you might ask? Well, this is Fido. And so Fido has features that resemble both Fifi and Pippin, but he's of course neither. So Fido is a Shar-Pei, yes. So that kind of looks like Pippin, but he also has a brown coat like Fifi. So a natural question is, what will happen now if we show this to our network? The answer is, honestly, anything could happen, constrained to our two outputs. So if the program was set up to only answer Fifi or Pippin, and again, this is sort of an inherent limitation that we baked in from the start, it's not going to be able to tell you that it's seen something new. This also, kind of comes back to the fact that this program, let's not get too carried away here. It's pretty remarkable the successes you can get, but this program has no idea what a dog is. It doesn't know who Fifi is, doesn't know who Pippin is. Ultimately, at the end of the day, to let a little daylight in on this fact, it's just mapping a splash of colors to a name. That name could have just as easily been Clifford and Rex, or it could have been 1 and 2, or it could have been, confusingly, Cat and Cat 2. And so it is possible for some models to know, have some sort of way of detecting, when they've seen something new. But by sort of construction, this one doesn't know the difference. And so this actually matters in real life too. So I also want to give one interesting case study of how this sort of process can go wrong. So there's this very interesting case where a team of researchers was trying to train an AI program to tell the difference between Siberian Huskies and wolves. And because they're superficially pretty similar looking, they're both like, grayish canines, and they were able to get some success in developing a model that could tell the two apart, but they wanted to understand why they were seeing certain errors, because it was doing very well on some data that they were presented and not so well on others. And after looking into their model more closely, they determined that their model was actually looking at the background and not at the dog, because the images of the Huskies were largely drawn from photos that people had taken of their dog in their backyard, and the images of the wolves were largely from the wild, like the tundra, up north. And so that's, even though the program had learned how to get mostly correct answers, it had done it in a way where it's sort of cheated. But it took a little effort to sort of uncover this fact. We weren't able to just divine it necessarily from watching the model do its work. And so, you can think of this as, your model is only ever going to be as good, partially, based on what's happening under the hood of the program, but also on the data set that you show it. So I kind of glossed over this detail earlier when I was talking about, our bank of photos. If they're large, the program might have just learned the rooms and backyards that Fifi and Pippin hang out in. And so this can matter a lot when programs are set to task on decisions that have a lot of importance on people's lives. For example, hiring decisions. If you were to try to train a program to sort of read someone's resume, let's automate the process of reading resumes. We can usually tell if we want to, give it a second look by a human or invite them to an interview, and we can also know when we want to throw a resume in the trash. And so if we, had a data set of resumes and decisions that were made by HR executives, to either forward them on or throw it in the trash, if there was some bias in those decisions, such as, if there is like some sort of discriminatory hiring practices going on, like perhaps if there was bias towards gender, race, other protected classes, if the model is shown data which originated from such a sort of colored process, then it will reproduce those dynamics, and they might not, the person using this model might not be as careful as the researchers with the huskies and the wolves. So it's important to remember just how this can kind of creep in if you aren't aware of how your data set sort of colors what you're doing and how your model's working. So what I just told you is only one way that computers can learn. And so the sort of jargon term for this is called supervised learning. And the reason why it has that term is because we are showing it we're showing it inputs and we're showing it outputs, and we say to the program, figure out the arrow in between, figure out your own rules for taking us from the input to the output. And so this can be useful for learning rules that would be hard for humans to communicate to the computer. And so there's another kind of twist on this, which is called unsupervised learning. So this is, when we give it lots of samples and relevant data, but we don't necessarily have answers that we're looking for. We say, find interesting patterns that we can work with from this data set. So one example is if we're trying to find patterns of something that, a data point that we would call normal versus data points that are anomalous, or that came from, that are kind of curveballs, that are surprises. Formalizing what that necessarily looks like into crisp rules can be difficult. And so I'll walk through an example, less so about how unsupervised learning algorithms work, but an example of where it might be difficult to construct a formal algorithm that, sort of conventional algorithm that takes into account all the different ways that something can, unexpected data can come at you, and how, AI might be useful in sort of attacking this problem. So one would be, this thing I just described, which is, given a sort of pattern of data, how do I know if a new data point is weird or sticks out in some unusual way? It would be detecting patterns of credit card purchases, for example, to detect fraud. So, no pun intended, but there's a wealth of data associated with individual credit card transactions, right? There's the cost that's associated with it. There's the time of day the purchase was made. There's the location of the vendor. So, for example, did you buy something in Boston? Did you buy something in New York? Was it on the side of the Mass Pike, etc.? The vendor itself is part of that information, like if it's a coffee shop, a bookstore. And you can also think of some combination of these previous ones being a category of purchase. So if it was like associated with food, beverage, or gasoline, or electronics, or a luxury purchase, right? And so there's a lot of different ways in which individual purchases could be normal or abnormal, but crucially, they'd also vary a lot for different people. So for example, all of us have our own purchasing habits that are, sort of define a normal for each of us. For example, I'm a graduate student. Mine tend to go a little bit more on the low end of the cost scale. My purchases I don't travel that much. My purchases are all largely, based around Cambridge. And they're often sort of purchases in the way of food or consumer goods, stopping in the pharmacy to buy toothpaste. But if you are in a rural area, perhaps you drive a lot more, perhaps your purchases are spread out over a large geographic area. Maybe you travel for work, and so you're going to be all over the place. There's a lot of different ways in which this can kind of get complicated by individual purchasing patterns. And so, one such example of a stream of purchases that might show up could be as follows. So suppose that this was my credit card transactions, where I buy ice cream in Harvard Square. I love JP Lex, it's great. I buy coffee in Central Square, Cafe Nero, delicious. Dinner in Back Bay, catching up with an old friend, going to a hardware store at Kendall on the way back from talking to MIT, buy a light bulb, get a hot dog at Fenway, diamond ring in Belarus, coffee at Longwood Medical Area, buy a donut in Boston Common. One of these patterns, one of these data points is clearly not like the others, right? And it's most likely, let's say that also this happened at 2 in the morning Eastern time or whatever, right? There's a lot of ways in which this could show up as unusual. But there's also a series of purchases in which this would fit right in with a normal pattern of behavior. So for example, if I bought an airplane ticket online, if I got a hotel, I booked a hotel in Belarus, I got dinner at Logan Airport, I bought Wi-Fi on the plane, I get lunch in Belarus, and then I get a diamond ring, that's just a vacation purchase. So, there's a lot of ways that, this sort of individual point could make sense. And there's a million different ways it could be normal. There's also a million different ways in which this could be abnormal, right? And so what's kind of cool, or part of the promise of unsupervised learning, is that AI can automate the process of, let's say, detecting, like flagging transactions by learning on, millions of different data, millions of different data patterns. Where you can see, not just one Canterbury grad student, but Visa's entire, credit card transaction database, for example. So yeah, okay, this is my crash course to AI. At this point, I'd like to pause if anybody in the audience had questions.
So one of the phrases I think it's supervised learning, is P or PD, say feedback to correct or incorrect.
Right.
It is automatically, you said. Who is automatically already kind of program?
Yeah, so there exists, a lot of people have done a lot of hard work in making sort of.
I mean, who is supervised?
Oh, okay. So sorry. So basically, the computer will feed the answer, or will feed the input in and look at the output and compare it against what it knows the answer should be. So the supervised comes with the fact that each photo of the dog comes with a name.
So somebody put the name or how to get the correct answer.
Right. Yeah. So this process, if you're going to go this like supervised learning route, you need to have not only the data, where here like is the image, but you also have the labels. So you have your input and your output to feed in. And yeah.
So database should have the answer in the process.
If you want to do it this way, then if you're trying to get from an input to an answer, if you're going to go this route, yes, then you need your answers. Yeah.
How do you use this to develop drugs for diseases?
So I'll talk a little bit more about how AI can feed into simulations, not for like drug design or discovery, that's a little afield for me, but there are people who are working on, in particular, to sort of just briefly steal my own thunder, you can use AI programs to kind of accelerate simulations or to sort of better analyze them. And so simulations of how like certain molecules, interact, like if they're stable or if certain configurations will be stable or not, that can be done on a computer, and AI can help with that. AI can also help with generating those molecules to then look at. But again, a little bit outside my expertise, so I don't want to comment too much on it. Great question, though. A lot of people are working on that. Yeah.
You mentioned like AI could be used to discover new materials. Can we talk about like how that process goes?
Yeah. So, actually, okay. This time I'll just take my word for it. I'll come back to it later.
Oh, okay.
Yeah. No, yeah. We'll get there. No, we'll get there soon. Yes. Please.
You said at the beginning of the presentation that AI can learn how to play chess.
Yeah.
Essentially, how is it able to do that with the supervised or does it play chess with supervised?
So this is a little outside my expertise, but I think that the way it works is that you would basically, so you would set up, like roughly speaking, the program would be set up so that, your input is a chessboard, your output is, the next move. And I think that the way that a lot of chess computers work is that they're able to sort of like look down, like sort of like down the road from a bunch of different possible moves. And so they can sort of figure out like, okay, if I were to take this pawn and move it here, what are all the ways the game can play out from there, and what's perhaps likely or not likely to happen. And then from there, it can consider many different like sort of paths at once. And so from there, figure out which ones are most likely to like leave the computer in a better off position, and then maybe make that move. This is like kind of like familiarity about having read about this once, but also I'm like kind of speculating about how this program might be set up. I don't know if it really fits into the sort of supervised, unsupervised framework necessarily. But yeah, that's an excellent question though.
When you were talking about how the computer programs learn tools, you talked about supervised learning and unsupervised learning, and I was wondering if there's other ways, and if those other ways, like the way that they learn, do they all follow a model input and output? achieving that?
Yeah. So, I mean, I guess this framework I'm just kind of introducing for the sake of this talk. I suppose there might be some that like sort of strain like that like rough definition. Yeah, there's definitely like there's sort of like other classes of machine learning and AI, of which unsupervised and supervised are just two. But yeah, there's more out there.
For unsupervised learning, you mentioned a couple of categories in the example that you used.
Right.
Are those the categories that the model itself would determine, or would those be influenced by the program?
That is an excellent question. So sometimes, the answer can be both. So the model won't know necessarily to work like you will have like sort of like with each data point an associated like cost. You will have the the vendor title, you will have the category of the purchase, etc. So those are all things that were sort of put there by the person who's like generating and curating this data set. One thing that you can also do is you can try to look for connections between certain data points that I just mentioned by sort of coming up with new ones that like represent like combinations. Like for example, like, oh, is the number of bedrooms times the number of bathrooms in the house like relevant to the price, or the number of like the square footage like square etc. Like sort of things that you derive from it. And so you can then also have you could come up with sort of like derived things from existing data, and then see if the model finds those useful or not. So it's one way that you can look for patterns. Is you can take. So to answer your question, one, you have to sort of feed in data that is curated in a certain way, so it won't necessarily know about data beyond that. But there are ways of sort of teasing out connections within that data that also require some input, but the model can help you with that. Yeah.
Is there a linkage between nanotechnology and AI?
Yeah.
Is it a subset?
So there has been some research recently into what's called like neuromorphic computing, which is like where this sort of like framework I just like described of like, okay, you adjust a set of rules in response to some like input and output, where people are trying to make like really tiny circuits that sort of model that framework. So they're kind of like basically like a little tiny like brain on a chip. So in a sense, it like mimics the structure of the brain and it performs computations like in that way. AI is also super important for like in some cases, helping out with simulations on the nanoscale. It can also be useful in processing data that comes in from experiments that are focused on nanoscale science. So I don't know, they're kind of, I would say they're like disjoint disciplines, but there's a lot of like interdisciplinary work that can come in applying, one to sort of like, have approaches inspired by AI in nanoscience or understanding nanoscience systems using AI. Yeah.
Could you, back to the chess question, could you get two AI computers playing against each other and use that to improve the rules it's using?
Yes. Amazingly, yeah, this is what that the aforementioned AlphaZero program did. So they had it learn Go as well as chess and maybe I think one or two other games, where it was never shown a human playing the game. The model just exclusively learned how to play chess by playing. I mean, they like taught it the rules and said like, okay, get to checkmate, you'll win. And then from there, my understanding is that they were just off to the races and it just played against itself, which is pretty cool. In a word, maybe one for oh. Oh yeah, please. Sorry, I didn't see you.
Well, for a facial recognition, they use polygons.
So my understanding, I mean, I think there's a lot of different ways that it could work. I think one way that it, like an algorithm could work would be by sort of trying to like figure out like sort of like parameters for somebody's face, and then like turning that into being showed a photo of me, like extract certain numbers of like parameters that describe my nose, that describe the shape of my forehead, describe the shape of my chin. And then from there, you can use that list of numbers to compare two faces and be like, is this likely to be the same person or not? If the numbers are severely different, then probably not. If they're very similar, then maybe the same face. That might be one way they can do it. Yeah, I remember reading about how some protesters are wearing certain masks that thwart facial recognition algorithms, which is pretty interesting. So sort of interrupting the way it would make sense of your face. Okay, so thanks for all the really good questions. And so now I'm gonna change gears a little bit and start talking about materials of the future, in short. So this part of the talk is largely going to concern material science for energy-based applications. But I'll start with talking about sort of what we are up against. But before that, some of you might be wondering, okay, I've heard of physics, I heard of chemistry, I heard of biology, but what is material science? So in short, material science is, a sort of very interdisciplinary field that involves methods from, physics, chemistry, engineering of all stripes. And it's largely concerned with understanding and sort of discovering and tuning properties of materials. And so I think, there's actually, a pretty remarkable success of material science in all of our pockets right now. I would call attention to the fact that, your phone has, scratch-resistant glass that is also receptive to touch. It can detect if you have 1, 2, 3 fingers on the screen, as well as how hard you're pushing. There's a tiny camera on it with millions of sensors that can achieve megapixel photos. And inside, there's a lithium-ion battery, which can be charged and recharged hundreds of times. In fact, the inventors of the lithium-ion battery won the Nobel Prize 3 weeks ago in chemistry for that. And so this is to say that, all of these things, they come from insights from many different fields. They're, incremental changes made over time by engineers who are committed to, one task or another. But the thing is that you don't necessarily taste flour, you don't taste water and batter. You just taste cake. All of these things, all these advances sort of invisibly improve your life. And they can come together to create, devices that you don't even think about how remarkable and wondrous they are. And so now for this next part, I'm going to talk about sort of the scope of the energy-based problem that we're facing. And then I'll talk about 2 sort of classes of materials that are the subject of a lot of scientific study. So in particular, catalysts, which I actually have done some work on, and another kind called ferroelectrics, more briefly. So let's talk a little bit about the scope of the problem. So this data set might look familiar to you. It was famously portrayed in a documentary starring a former vice president. But this is the trend of carbon dioxide increase over time, as measured from an observatory in Hawaii. And so the thing is that our modern society is largely powered by carbon-based fuel, the carbon from that, which ends up in the atmosphere in the form of CO2. And so the thing is all of these, this sort of trend over time arises from the sum total of billions of people, making their way on Earth every day, all the global economies in the world, my bus home tonight, your breakfast tomorrow, etc. This is all down to carbon, almost entirely down to carbon-based energy. And so even if the problem has been made up of, trillions of little footprints, like all these activities, like my use of my laser pointer right now, the solution can also be made up of trillions of little handprints, both through, collective action on individual levels, but also technological advances in a bunch of different directions. So this is to say, I'm not going to be able to say, this is it. We are working on the wonder material that is going to solve all of this. What I'm going to describe is a few things that, might make very real gains that will be part of the solution. And, how AI can help us find better ones. So some of the targets that might be enabled by new materials include, making existing industrial processes more efficient. A lot of the energy in the economy goes into, industrial processes that generate chemicals that then, go into, paint, glass, batteries, etc. And so, we want to take our sort of traditional industrial processes and maybe put them on a diet. So we can get away with, using fewer calories. But also, materials might enable new ways of generating energy as well. So, the sun is, a central source of energy for our solar system, not the central. And, plants have already gotten wise to the fact that sunlight plus CO2 can be a valuable energy source for photosynthesis. There are people who are working on making what are called like artificial leaves that help to turn CO2 plus sunlight into fuel, which because that carbon came from the atmosphere, once it gets burned and then re-released in the atmosphere, because the carbon that we put out was carbon that was already in the atmosphere that we just temporarily changed over to fuel, aided by our material here, the whole process is carbon neutral. So this is a closed loop. So if we want to accomplish tasks like this and many more, we'll need futuristic materials. And so a natural question is, where are we going to find such materials? The answer is, simplistically, somewhere here on the periodic table. All right, that's my time. Thank you very much, everyone. But yeah, no, this is just the beginning, right? There's a lot of different elements out there, and the solutions are going to come from putting them together in clever ways with certain, certain like recipes for preparation, right? And so materials discovery is actually a really, really challenging task. So a very, very famous example that comes up often in sort of the material science community is the sort of Edisonian way of discovering materials. So named because of the story of reportedly how Thomas Edison discovered a material for the filament in the electric light bulb, that it took not just one try, not just 5, not 20, not 40, 60, 160, or 640 different attempts, but all of those twice over. And in fact, around 2,000 different attempts before finally finding a formula that worked. And so what we want to do is to try to accelerate the pace of discoveries, because there's been some empirical evidence that it takes for a bunch of different technologies about 20 to 30 years to get from this first initial breakthrough in some isolated laboratory to actually reaching the market, to then finally reaching ubiquitous usage. Where all technologies like cars, jet planes, even the humble lithium-ion battery that's one on my desk, in my pocket, on my wrist. It had to start first in a lab, and then it had to get commercialized, and now it's everywhere. And so ideally, all the wonder materials that I cited on my wish list, we would have them yesterday. And so what we want to do is to try to compress this interval between when something gets invented and when it can actually be see use in the market. And in particular, with this part right here, where we're trying new materials to find ones that will be like industrially feasible. And so what I'm telling you is that the sort of 21st century way of discovering new materials, at least the one that I'm focusing on, is to perform thousands of attempts on the computer. So at a fraction of the cost and tens to hundreds of times faster, we can actually just loop through using high quality simulations a bunch of different materials that we can then hand off to our experimental colleagues and say, okay, try these ones. And then from there, working from computer simulated predictions, we can maybe hand off predictions that can then lead to better catalysts, better thermoelectrics, better batteries, etc. So I'll demonstrate an example sort of problem that we might want to go after with an industrial process that actually matters a lot to you 3 times a day. In particular, I'm talking about the sort of energy cost of fertilizers. So, the job of fertilizer is to get nitrogen-based chemicals into the ground so they can facilitate the growth of some crop. But the fertilizer maker's job is to try to get those nitrogen-based chemicals from a chemical reaction which unfolds on a special material. And so the thing is that facilitating this chemical reaction, which is intimately connected to agriculture, takes a lot of energy, right? You can think of it as almost like cooking, right? Like, cake batter doesn't just turn delicious on the counter, you have to throw it into the oven. And then the energy helps to facilitate the chemical reaction that you care about. So turns out that fertilizer production is about 1.2% of the world's energy consumption. And so, natural question is, when we're talking on the scale of the entire planet Earth, how much is, a humble 1.2%? Turns out it's about equal to a light bulb left on for every man, woman, and child on Earth for an entire year. So any sort of materials that we can provide that can help take a bite out of this energy cost while still feeding 7 billion people would be an absolute win. So this leads me to my first sort of material case study, which is catalysts. So you can think of this as a chemical party or dance floor. So you may have heard the term catalyst get thrown out in other contexts. Basically, in the chemistry sense, it helps to accelerate a chemical reaction that we care about. And so I will illustrate a sort of analogy to how catalysts work with the process of facilitating chemistry at a party. And so I mean intersocial chemistry here. So let's, here's a few states that you can find yourself in at a gathering. You can be talking to nobody, which, that's easy enough. You can stay there for a while. Small talk, starting a conversation, that's hard. That can be difficult, especially if you're shy. But then once you're having a nice chat with somebody, you're having fun. And that's what you came here to do. But it's getting over this hump that's the hard part. So if you are playing host or hostess, one thing that you can do to help facilitate the motion of people from the talking to nobody state to the having a wonderful time state is to, for example, set out pizza and beer. That will get people talking. You get people sort of lining up to grab it. They can mingle with one another. They can be like, "Oh, you love Hawaiian?" It's like, "Oh yeah, totally." That's another scientific fact. Hawaiian pizza is great. They can sip beer. That gets people loosened up. And so that brings down the cost of the sort of effort cost of starting a conversation, which means that people will organically start to move from this talking to nobody state to the kind of small talky state, and then hopefully if you're lucky, people will then move into having a nice time. And now your party's a success. And even if sometimes starting a conversation doesn't go so well, sometimes people will move backwards. That's okay, as long as we're getting people on the aggregate over to here, then we're doing good. All right, so it turns out catalysts work kind of in a similar way, except with facilitating chemical reactions, where, for example, we have nitrogen in the air here in its very much happy place. It's a little less happy over here in remotely form, but that's where we want it. And so it turns out that nitrogen that's about to react is in its sort of energy or effort unhappy place. And so if we can provide a catalyst for the reaction to sort of unfold on, then we can bring down the cost of getting it, sort of energy cost of getting nitrogen in this about to react state, and then maybe we can start to move over from where it's in a form that's kind of useless to us to a form that's very valuable, that ends up eventually on your dinner plate. So how do simulations help us? So we can actually use simulations on the computer to do really, really, really in-depth studies of how molecules interact with catalysts and how reactions play out sort of on the surface. So I like to think of this as studying sort of choreography of a chemical reaction, because it's kind of a visual process where something will come in, maybe molecule orients this way, which then now it's interacting in a slightly different way, and then something can jump off here, something can jump on here. And this way, a catalyst is like a chemical dance floor. And so simulations help us do a few things when we're studying catalysts. They help us better understand good ones that are already in practice. We can ask why and get a clearer picture by sort of figuring out how reactions unfold on the surface. We can improve existing ones by sort of putting in hypothetical modifications and seeing if that improves or weakens the reactivity. And we can discover new ones, things that, materials that nobody has looked at for certain reaction. We can sort of demo it on the computer and see if it looks like that molecule will undergo the sort of dance that we want it to on that surface. And so, if we want to eventually perhaps steal Planck's greatest idea, if we want to have a material that can perform photosynthesis, an artificial leaf, if you will, something where, sunlight plus carbon dioxide can then, turn into a usable fuel, and from there, we're off to the races. Computer simulations are a great start. So I'll briefly comment on a different kind of material that's also kind of it's gotten some industrial attention, and it's kind of a neat example, and also come back later. And they're called thermoelectrics. So imagine, you get home after this talk, and you sit down with your laptop, and you start using it. And you check your email, you maybe look up a video on YouTube, and you start, checking, your instant messaging applications, and then something will happen with your laptop. Namely, it will start to generate heat. You'll notice this if it's on your lap in particular. But the thing is your laptop's job is not to generate heat. Its job is to, identify your dogs for you, but also, or do all those other things. But the heat is merely the byproduct, right? So the thing is that there are actually certain materials that can generate electricity when there's a heat imbalance within the material. And so how it happens, I won't necessarily go into detail, but these are called thermoelectrics. And sort of roughly speaking, if it's hot on one end, cold on the other, electricity will start to flow. And so then from there, if we had thermoelectrics that were cheap, that were cost effective, that were made out of non-toxic and readily abundant materials, if thermoelectrics could be in a bunch of common devices, maybe we could start to recycle heat sources from all over. So maybe we could make one, for example, electric cars are more efficient if it harvested sort of waste heat that comes off the engine to turn into electricity that goes back into the car. So yeah, that's my summary sort of a reason why I think material science is really exciting for energy applications. A few classes of materials that are really relevant to addressing real problems with energy. And now, in the next part of the talk, I'll talk about how AI and material science come together. But before I move on, I'll also bring for any questions that you guys have.
Is the fidelity of simulations of catalysts sufficiently good that the predictions they would give you today would be useful for filtering a candidate set of materials?
Surprisingly, yes. Actually, yeah, we can. We're actually, due to advances in software and hardware over the years, doing simulations of how molecules interact with surfaces that captures almost all of the sort of quantum physical detail is pretty routine now. And there's thousands of research papers every year that are studying reactions like that closely. And so, yeah, there is actually a lot of success both in using simulations to extract trends and also make predictions on how to optimize existing catalysts.
Has your research already had success identifying materials suited to the CO2 conversion?
So we actually am involved in a project that is part of this artificial leaf quest. And so we haven't gotten any experimentalists to look at it yet, but I mean, we might have some materials that no one has looked at for CO2 reduction that have some properties that look promising. But there's a lot that needs to happen. It's like an egg race, you know what I mean? Where you have a scientific, you have a scientific idea that it needs to hold up to theoretical scrutiny. It needs to be able to work in the lab, and it also needs to be practical for it to affect human welfare writ large. And so getting one material through all those hoops is why it took 2,000 tries, for light bulb. It's why it's going to take a while. But if we can just spur up ideas that can be used, that's also kind of open. And so yeah, there has been some interesting. I'll talk a little bit in the back half about some interesting results about thermoelectrics. But yeah. Okay. Yeah.
All right, so it's 8:02 now, so we'll give you guys about 5 minutes. You can get up, stretch your legs, use the restrooms, grab a flyer or a postcard if you didn't on your way in, and we'll get started up now. It's 8:03, so we'll get started at 8:08. Okay. Yeah, sorry, I hope that wasn't too many questions. I didn't want to cut them off.
Yeah, that's good.
Okay, good.
So I listened to the lecture.
Do not agree. Oh, cool. At least one is from the board. Yeah. Yeah, definitely. So one thing. Yeah, a lot of the monitoring is really good software and hardware.
Yeah, no, but.
Right. Yeah, like Moore's law. Yeah. What are the- People, I can tell you, there's a lot of people who study batteries on their computer, like by just watching how, like, for example, lithium diffuses through your electrolyte. And there's people who do every stage. They try to understand how lithium feeds into the cathode. They understand how, they're trying to understand how, like, one of the problems with batteries sometimes is that, like, so, like, the road structure, the electrolyte interface, called dendrites, because you can on fingers, they go up and down. So the idea is that if you go under the battery, it shorts it, and you're in big trouble. And so there are people who write, so they're used to the anodes, the electrolytes, the cathodes, the interface, there's a lot of different stuff at play. There are also people who, there's a really cool study about using ML to predict battery lifetime from watching it charge and discharge a few times to accelerate battery research. So it's almost like if I showed you a baby, you know, guess their mileage. Like that's what it is. They're showing taking their first steps. Like that's what it is. They have a lot of data how charging and discharging like sort of predicts long-term battery lifetime and like how like the response changes. It's really cool. Yeah. Yeah, me too. Really cool.
So, about the material science, I'm guessing they should probably use like the AI for that. Like they would develop things medical devices that probably with but also I work where they do a lot of time whether it's vegetable devices as well. They want we like that are
The construction.
Yeah. That way, like there will be good kind of those future like how all of this.
Yeah, no, I mean, like, one of the things that when you're doing, like, sort of materials, like, scraping, like, if you're writing a bunch of these calculations, you can just say, like, you don't want, like, even if it would make a really good, like, catalyst, like, that's possible. Like, you can exclude, like, you can also filter it down to, like, low-cost ones, Yeah, it's kind of part of the magic of doing it. Very high upstream, only study ones that you think will be less likely to. Yeah, I don't know. Whatever AI can be used like quality assurance too. Even if there is something toxic in there. I don't know. Yeah, I don't have no experience with it. Guess too much about the medical devices, but yeah, if it gets your imagination going. That's awesome.
All right, we're gonna give us a couple more seconds to get settled back in your seats, and then I'll turn back over to Stephen for the rest of his talk.
Just say when.
Yeah.
Okay. All right. Thanks for the questions in the interim. I hope you guys got to stretch your legs, take a nice break. And so now we will go to the thrilling conclusion of this talk, which is all these things I set up in the first two. I'm going to come back and talk about how they can actually be used for materials discovery and facilitating simulations. So let's talk first about the simulation piece. So simulations, as mentioned before, are really cool because they help us plan experiments. They can help us discover new materials. They help us better understand why existing great materials are great. And pretty critically, when you're doing high quality, full fidelity simulations, oftentimes you get bottlenecked by how long they can take. And so the faster we can do these simulations, the better. So now the natural question is, how does AI help us accelerate simulations? So let's talk first about movies and what a movie is. Remember that a movie is a series of still frames, and perhaps you've seen this image before. It's a pretty iconic series of photographs that were taken in the late 1800s as one of the first real cool sort of like it's kind of a killer app of like photography, demonstrating that not only you can make a cool movie of like a horse running, but actually this was commissioned as a scientific study. Fun fact. So this series was commissioned by Leland Stanford, whose son is actually the namesake of Stanford University out in California. And the question that they wanted to answer is there actually a point in a horse's stride where all four hooves are off the ground at the same time? Answer, yes, at this point. That's pretty cool. So this is an example of how movies can help us develop scientific insights. And so, how they got this movie came from, they had to get a horse, they get the rider, they had to set up the camera, which at the time was no small feat. They'd have to, take lots of photographs, film it, they then develop it. This is kind of a labor-intensive process. But if we had access to this movie and we could study these in depth, if we were to become an expert in this sort of subfield, like let's say if you were a sports veterinarian, right? Like you were an expert in like how horses run. Expertise gained from studying these movies. From one frame, could you guess maybe what the next frame would be? I think that if you actually study this as like for your job, you could look at this and probably peg where it is in stride, or if not, where exactly, be like, okay, I think I know what's going to happen next. From there, you could think like, could we fill in the gaps? Could I show you two photos and you'd be like, oh, okay, yeah, I've seen this before. Yeah, I can tell you what each leg is going to do from this point in stride to this point in stride. So this sort of ability to look at one frame and orient yourself and figure out what's going on and to fill in gaps between frames, this comes from expertise. And so we can find AI programs that can kind of help us do both. And the reason why I'm bringing this up is because studying molecular movies is a big part of my job. Molecular movies on the computer help us learn how reactions proceed on a surface, right? And so, how does this help? It's exactly the same as with Mr. Stanford and his horsey back in the 1800s, where there might be a certain part of the reaction that we really care about. We want to catch it in the act so we can better understand how it will play into the overall reaction. For example, when I was talking earlier about nitrogen and the sort of like, it's in one happy place, it's getting to another happy place, it's going through an uncomfortable in between, the sort of chemical small talk. This would be an example of us catching a certain reaction in the act, or be watching it go through that process, so we can understand how to make it easier for our reaction to proceed along that pathway. And so we generate these movies and study reactions by using the traditional rules-based programs that I was talking about earlier on in the talk. Right, so this is stuff where physicists have sat down, they've written programs that use the laws of physics to from one configuration of atoms in a molecule or on a surface, you can figure out what happens next. Then you generate your next frame of what happens next, and then you repeat ad nauseum, where you calculate what happens next, and you take it there, and then so on, repeat, and that generates your movie. Ultimately, just a series of still frames. So if we had an AI program that was sort of designed to look at frames from molecular movies and then understand where it is in the process, guess the next frame, that could be very useful. So before I tell you about how these programs would work, I'm going to pause to explain a mathematical concept that kind of underpins how these programs function. And so this concept is called interpolation. So interpolation is basically figuring out how new pieces of data fit into an existing pattern. So one example of simple interpolation between two shapes stands before you. So you can imagine that we would put in new shapes sort of along this axis of more circly versus more squarish. So here are three new shapes, and if we wanted to sort of like imagine interpolating them between circle and a square, we could, let's start with this one, right? So this guy, it's got four straight sides, and it has rounded curves where, all the circle is round, all this is rigid and straight. But, even though it has round parts, it looks more superficially like a square, and it has a lot of like straight lines. We can put it more over here. For this guy down here, okay, it's like 75% circle. And certainly this part does resemble the square. It's like 25% square. I would say that this is more circly to my eye. And then this one is somewhere in between because, okay, it's also, it is a polygon. It's made up of sort of sharp lines intersecting at angles. But at the same time, like it's clearly rounder than the square is. One would imagine if it were, if it were even finer, it would start to look like a circle. So I would put this one as somewhere in between. And of course, you may disagree with the way I classified these. But this is just to show like what one example of interpolation could look like with a simple mathematical object. The thing is that interpolation can also happen in very abstract ways. And I argue that humans actually are capable of abstract interpolation all the time, every day. One example is, are my parents. That's my mom on the right, my dad on the left. For the sake of this exercise, I'll point out that my dad used to have a brown hair. But if you were to try it, so this is, your presenter and my siblings, and you can interpolate between, two parents and sort of, figure out where children fit into a sort of in-between pattern. I mean, this is something that is, kind of a complicated task, like looking and, judging how individual shapes resemble one person or another. But again, this is something pedestrian that we all do every day. And, no one had to really teach you how to do this. And so, I showed you the answers that I came up with in the previous one. The answers here come from an expert panel of aunts and uncles. Hotly debated at the holidays. But yeah, this is how the sort of canonical ranking goes, where I look the most like my mom, sister the most like my dad, and brother somewhere in between. So back to our movies. So could this notion of like interpolation help when we want to fill in the gaps? Answer: absolutely. So what, at least the stuff that I work with day to day, our AI program is ultimately interpolating in a sort of like abstract way, except instead of like horses running, it's molecules in action. And so our input here would be a new frame. And here, our program would have a data bank of frames that we've computed using our, conventional rules-based laws of physics, sort of time-expensive but high-quality simulations. And our program can then loop through and figure out a way to, sorry, this is a little washed out, compare how each frame sort of like it to all the other frames that it's seen before. And then from there, it's fitting it into this pattern that's established by this data bank. And then it gives you the next output frame. And so then from there, once we've sort of, set up this process very nicely, we have a solid data bank of frames, and we have a program that's well trained to sort of predict the next one from the existing one. Then we're in business. So a model that fills in the gaps can eventually predict sort of entire movies. And so you can think of this as fast forwarding our molecular movies, which in short lets us learn more faster. Okay, so the last example that I'll talk about today is a study that it was done by a group that I've done some work with, and I just think this thing's the coolest stuff since sliced bread. So basically, the name of the game is discovering materials by association. So a natural question is, how would a computer ever learn association between sort of like ideas, objects, entities, whatever? So like this concept already exists in English, right? When we say the phrase spoken in the same breath as. So for example, let's talk, three sort of hypothetical conversations that you might overhear, or things you might oversee, like in a magazine, or like, rock legends like Jimi Hendrix, Rolling Stones, Frank Zappa, or famously innovative guitarists, B.B. King, Frank Zappa, Eddie Van Halen, or, my dad loved all the classic rock music, Pink Floyd, Steely Dan, Zappa, even, without having heard of Zappa or knowing who he was, if you are aware of or familiar with, the stuff that is often mentioned in the same breath, then, that's kind of a clue that you might actually like his music if you were to give it a listen. And the same thing applies with other sort of, forms of media, like, if we were to take, gangster movies or conversations surrounding a particular actor or maybe a director, even if you had, if you were a Scorsese fan who had never seen Goodfellas, you'd be like, oh yeah, even if you don't even know necessarily, what's behind this, you might just be like, oh yeah, Goodfellas, might be a movie I like if I happen to, like the actor or like the sort of affiliated movies that are mentioned in the same breath. So to talk about how we can sort of think about association mathematically, imagine this. Suppose that we had a program that could sort of read articles and identify when different artists were mentioned in all the variety of different, complicated ways that can come up. And could also, and could sort of like tag them and keep track of mentions as well as, artists that are mentioned in the same breath. Let's say the same sentence, same paragraph, even same article, right? And so let's say we had this program read like 50 years of Rolling Stone magazine. Eventually, we could produce an association map where all these artists that I put on the previous screen could be lumped together, where they would spatially be organized, where artists that are closer together are ones that were mentioned together more often. This kind of makes sense. Imagine that if you were reading, popular music articles, you would see that the Beatles and Rolling Stones are often mentioned together, and the Beatles and Kanye West would not often be mentioned together. Even less so for Kesha and Eric Dolphy. From there, you would naturally see, just by the way these things work, clustering, right? Where there would be discernible patterns that, if you sort of knew, what genres these guys belong to, you could start to see that association, this sort of conceptual association would give rise to, critics mentioning them more often together. And so, right, you would see like, jazz artists, 80s rock artists, hip hop, 2000s pop, like all these genres would cluster together. And you could actually use this to make, a music recommendation service or algorithm where, I could generate one such map and then we could fill it in where the green ones would be artists that you know and like, red ones being ones you don't like, and transparent ones being, artists that you hadn't considered yet. And so if I wanted to suggest to you a new artist, a good place to start would be to sort of look around the ones that you had already said that you like. So if you like a little jazz, you like some 80s rock, but you're a big fan of classic rock, one might reasonably conclude that because that sort of comes up in the intersection of these, you might want to give them a shot. So here's where it gets crazy, is that there's actually a really neat study where they made a program called Math Scholar that was trained to be able to read summaries of scientific papers or abstracts. And so basically what Math Scholar did was it looked through millions of different research papers. It kept track of materials that were mentioned as well as functions associated with those materials. And then it looked for this sort of natural clustering by the function of materials, and then it looked sort of around those clusters to try to discover new materials by function. So to recap, whereas before we had, it pouring over like popular music magazines, and we had a bunch of artists, here this would be looping through scientific papers and keeping track of a bunch of different materials. And so then from there, they actually found that they're, visualized in a certain way, you would see clustering by genre of materials, where, battery materials would show up in one place, thermoelectrics would show up in another. Those that are materials that are famous for, existing one dimension, two dimensions, whether they're flat, those all showed up together. And basically, they were able to show that they could sort of trace the discovery of thermoelectrics over time by sort of generating these association maps at different points in the history of the scientific literature, and then looking around that cluster. So basically, what they were trying to argue is that you could then look around the existing set of thermoelectrics, point to an adjacent material, and be like, okay, we should look at that one to try to discover a new function for this material. Okay, so that's all the content that I wanted to talk about today. In conclusion, AI, as it stands today, is mostly programs that are learning their own rules or patterns. Kind of, again, in the blind, our program didn't know what PT is, but based largely on data. Futuristic materials can help to make society more energy efficient, and AI can help to accelerate the scientific process and help to augment our intelligence as scientists. So thanks very much for your attention.
Feel free to stop by and ask any last-minute questions of the speaker on the way out, and we hope to see you again at a future event.
It seems like